Hi there. I want to help you get the most out of HEC-RAS bridge modeling. We're going to be using HEC-RAS for this tutorial, but you can apply these same tips and tricks to the U.S. Army Corps of Engineers HEC-RAS software. Now at the end of this tutorial, you'll be more skilled and better equipped to handle a wide variety of bridge modeling projects. Now the information I'm going to present in this tutorial video will give you insight and a better understanding of how to best create and develop a HEC-RAS bridge model. So be sure to watch the entire video so you can see all of the step-by-step instructions and engineering tips that I provide on how to become a master at HEC-RAS bridge modeling. And be sure to subscribe to our YouTube channel so you can stay up to date with all the engineering tips and tricks videos that we provide. Now finally, if you have not yet started using HEC-RAS, visit our website at CivilGEO.com and download a copy so you can follow along with this tutorial. Here is a location where we need to model an existing two-lane bridge. Ultimately, we will need to figure out the potential bridge scour that can occupy this roadway crossing, and we will need to determine what is involved in upgrading the bridge from a two-lane to a four-lane bridge. But for this tutorial, we are just going to model the existing bridge. The first thing to do is define the river reach. There are various ways of defining a river reach, but we will use the Draw River Reach command for this bridge tutorial. Notice that the software automatically places us into a 2D view mode and will create a curvilinear polyline so that the digitized river reach looks more natural. Once we start to digitize the river reach, the software prompts us on the status line at the bottom of the screen to digitize the river from an upstream to a downstream direction. As we digitize the river reach, you can see that the polyline representing the river reach is drawn as a smooth curve. Now, if we accidentally digitize the river reach in the wrong flow direction, from a downstream to an upstream direction, we can easily reverse the flow direction of the river reach. When we are finished digitizing the river reach, right-click and choose Done from the displayed context menu. We are then back at the Draw River Reach dialog box. Next, we need to define the name of the river and the reach. This is the Cuyahoga River, and we will call this reach the Lower Falls. This river is downstream of a dam outside of Akron, Ohio. After the river has been defined, we are ready to define the cross-sections that will be used in modeling the bridge structure. HEC-RAS requires that a minimum of 4 cross-sections be defined whenever you are modeling a roadway crossing containing a bridge or culvert. 2 cross-sections are defined downstream of the roadway crossing structure, and 2 cross-sections are defined upstream of the structure. However, you can define additional cross-sections, and many times these cross-sections are necessary upstream of the roadway crossing to account for additional backwater created upstream of the roadway crossing. The 2 cross-sections that are adjacent to the roadway crossing are placed in the full valley area adjacent to the roadway embankment. They represent the geometry of the river valley without the roadway embankment, which is the roadway fill area. We call these cross-sections the upstream face cross-section and the downstream face cross-section, since they are so close to the face of the roadway crossing structure. The cross-section that is upstream of the upstream face cross-section is called the approach cross-section. This cross-section is placed upstream of the roadway crossing at a far enough distance where the impact of the flow contracting inward through the bridge or culvert opening is no longer being felt, and all the water molecules, at least I like to refer to it this way, are running parallel to each other. The distance that the approach cross-section is offset upstream from the upstream face cross-section can vary based upon the geometry of the river overbank, the speed at which the river flows, and other site-specific conditions. However, a rule of thumb you can use is that the flow contracts at a 1:1 to a 2:1 ratio. So if the overbank flow on one side of the river needs to contract 100 feet inward to get through the bridge opening, you will want to place the approach cross-section at a distance between 100 to 200 feet upstream of the upstream face cross-section. Again, this is a rule of thumb and is subject to change based upon the local conditions being modeled. The cross-section located downstream of the downstream face cross-section is called the exit cross-section, and is placed at a distance far enough downstream where the impact of the flow expanding outward is no longer being considered. Again, as I described earlier, it is where the water molecules are running parallel to each other. The distance that the exit cross-section is offset downstream from the downstream face cross-section again varies upon the site conditions. However, the rule of thumb that is typically used is that the flow contracts at a 2:1 to a 4:1 ratio. So if the overbank flow on one side of the river expands outward 100 feet, then the exit cross-section is placed between 200 and 400 feet downstream of the downstream face cross-section. The flow requires a longer travel distance to expand outward on the downstream side of the roadway crossing than it does to contract inward on the upstream side. There are different ways to define cross-sections, but in this tutorial, we will use the Draw Cross-Section command for defining the cross-sections. From the displayed Draw Cross-Sections dialog box, we can specify various options. We can define the elevation data source that we're going to use for extracting the cross-section geometry. In this example, we are going to use the underlying AutoCAD Civil 3D drawing. However, you can use a MicroStation drawing file, elevation grid, GIS data, LiDAR data, geopack terrain model, inroads terrain data, TIN data, and other elevation data sources. We can define other information, such as how the bank stations are to be defined. In this example, we will define the bank stations at a 3-foot channel depth and provide a maximum search distance of 300 feet to acquire that 3-foot depth. In addition, we can determine how we want the cross-section IDs to be numbered. In this tutorial, we will specify that the cross-section IDs be numbered with river chainage in feet units. But you could have cross-section numbered with river chainage in miles, metric SI units, or sequentially. To create a cross-section, click the Draw button. The dialog box temporarily disappears. You can then draw a polyline on the map view where you want to place the cross-section. For bridge projects, I like to start out by defining the upstream face cross-section, which is on the immediate upstream side of the roadway crossing structure. As I described earlier, this cross-section is defined in the full valley region adjacent to the upstream roadway embankment. If you can see elevation contour lines, then it is much easier to determine where to place this cross-section. You can draw the cross-section from left to right, or right to left, does not really matter. The software will figure out what you're doing. As you digitize the cross-section polyline, simply click where you want to set a pivot point or anchor point to change the direction of the cross-section polyline. When you are finished drawing the cross-section polyline, right-click and choose Done from the displayed context menu. You are immediately returned to the Draw Cross-Sections dialog box. Notice that the software has automatically assigned the ID to the cross-section we drew. Click the Generate button, and the software will extract the geometry for the cross-section from the defined elevation terrain data source. Next, let's define the downstream face cross-section along the downstream side of the roadway crossing. For this cross-section, I'm going to draw it in a direction opposite of what we did for the previous cross-section. Again, the software will figure out what you were doing. You do not need to worry about the direction that you draw a cross-section. However, we need to be careful. We need to digitize close to the downstream roadway embankment without digitizing into the river that runs alongside the roadway. Again, when we are finished, right-click and choose Done, and we are returned back to the dialog box. Notice that the software automatically numbered the cross-section ID based upon the river chainage. We can choose to accept the suggested cross-section ID or change it if we want. Click the Generate button, and the software will extract the cross-section geometry and create the cross-section. Okay, now we need to draw the remaining cross-sections. Upstream of the bridge, we can see a wastewater retention pond that is used to temporarily store any excess wastewater that the plant cannot process during a storm event. It is used to hold any possible overflow that might otherwise occur. Since this structure tends to constrict the flow as it travels downstream, we're going to place the approach cross-section here. And I will place a couple of additional cross-sections upstream to account for any additional backwater that is created by the roadway crossing. On the downstream side of the roadway crossing, we have a tight bend in the river as it makes a 90-degree turn alongside the roadway embankment. We need to account for that bend by drawing the exit cross-section perpendicular to the flow. Now, if you make a mistake or change your mind while digitizing the cross-section polyline, simply press the backspace key or press Ctrl-Z, and you can backstep the digitizing you have done one segment at a time. And in order to correctly determine the normal depth energy slope for the downstream boundary starting condition, I will place another cross-section a bit further downstream. Because there is such a tight bend where the roadway crossing is located, we need to define the overbank flow lengths to accurately model the friction losses as the flow travels downstream. There are different ways to do this, but one way is to draw polylines that represent the overbank flow and then assign those polylines as the overbank flow lengths. From the Map Edit ribbon menu, select Draw Polylines, and then draw curvilinear polylines. We will then draw a polyline on the map view along the centroid of where the overbank flow resides. I generally perform this step later, after I've generated a flood map, so I can more clearly see the extent of the overbank flow area. You do not have to draw the flow length polylines for the entire river reach, only in the region where the river bend occurs. Next, return to the Input ribbon menu and select Assign Entities, and then Assign Flow Lengths. From the displayed dialog box, click the Pick button to select the overbank flow polylines we drew. Select one of the polylines and you will see it glow on the screen. Next, right-click and choose Select Similar from the displayed context menu. The software will then automatically select the other polyline. Then right-click and choose Done, and we are returned back to the dialog box with the two overbank flow polylines selected. Next, click the Select All button to select all the cross-sections in the project. In the background, you can see the cross-sections selected on the map view. Finally, click OK, and the software will compute the overbank flow lengths for the cross-sections that intersect the two overbank flow polylines we drew. We can check the downstream flow lengths that have been assigned to the cross-sections. From the Input ribbon menu, select Cross-sections, and then Edit Flow Length. The software displays a dialog box with all the cross-sections and their associated flow lengths. Here we can see the downstream flow lengths that have been assigned to the cross-sections for the left overbank, channel, and right overbank. Flow lengths are always defined from the current cross-section to the next downstream cross-section. We can clearly see the change in flow length where the river bend occurs. Let's turn off the drawing layer to hide the overbank flow length polylines we drew. The next step is to define the roadway crossing structure. From the Input ribbon menu, select Roadway Crossings. Now there are different ways to define the roadway. For example, if there is already a roadway centerline or feature line representing the roadway, you can use the Assign Roadway Crossings command. In this project, however, we do not have a roadway centerline. Therefore, we are going to draw the roadway crossing centerline. Select the Draw Roadway Crossings command. We see from the displayed dialog box that we can extract the roadway geometry from the previously assigned digital terrain source. And if we want, we can create a curvilinear polyline to more accurately follow the horizontal curvature of the roadway. To create the roadway crossing, click the Draw button. Again, you can draw the roadway center polyline from left to right or right to left. It does not matter. The software will figure it out for you. As you are laying out the roadway, try to follow along the center line of the road. Click to add points of curvature along the roadway. Again, if you make a mistake, press the backspace key or Ctrl-Z to back up the digitizing one segment at a time. Once you have completed digitizing the roadway centerline, right-click and choose Done from the displayed context menu. You are returned back to the dialog box. Next, we will define the roadway width at the bridge opening. From the Roadway Width entry, click the Pick button and measure the roadway width at the bridge opening, parallel to the flow of the river. In addition, we need to measure the distance from the upstream side of the bridge opening to the upstream face cross-section. From the Distance from Railing to Upstream Cross-section entry, click the Pick button and measure the flow distance from the upstream face of the bridge to the upstream cross-section, again, parallel to the flow. Once these two measurements have been defined, click the Apply button, and the software will create the roadway crossing. Since we are defining only one roadway crossing for this project, click the Close button to finish. Let's look at the roadway crossings that the software constructed. Double-click the roadway crossing, and the Bridge and Culvert Data dialog box is displayed. Something that I find to be a great help is to adjust the bridge opening horizontal stationing so that the stationing is the same for both the upstream and downstream face cross-sections. That way, I can use the same horizontal stationing for bridge piers, sloping abutments, ineffective flow areas, and culvert center lines. From the panel drop-down selector, choose Geometry Adjustment. From the displayed panel, choose the Shift Stationing option and select either Thalweg, Centered Between Banks, or river reach intersection option for defining the horizontal stationing. For this project, we will choose the river reach intersection option, which corresponds to the blue triangle shown at the bottom of the bridge opening. Then, specify the horizontal station to be assigned. You generally want to keep the cross-section horizontal stationing as positive values, so choose a large enough value. For this project, we will define the horizontal station as 1000. Next, check the checkboxes to adjust the horizontal stationing at both the upstream and downstream face cross-sections. Then, click the Apply button, and it's done. You can see that the horizontal stationing is the same for both the upstream and downstream face cross-sections. Next, we are going to define the bridge opening. There are different ways we can do that. However, for this project, we are going to have the software automatically construct the bridge opening based upon surveyed bridge opening dimensions. First, we're going to remove the implied bridge opening from the cross-sections. While this may look like the actual bridge opening sloping abutments, it is not an accurate representation of the opening. This representation was created when the LiDAR elevation data was processed and was stripped to bare earth. Select the Remove Roadway Geometry tool from the toolbar. Then, draw a box around the roadway geometry points that we want to remove. Do this for both the upstream and downstream bridge opening. Next, from the drop-down selector, choose Build Bridge Opening. From the displayed panel, we are going to define the bridge opening low chord elevation. Now this bridge has a sloping bridge deck. For the low side of the sloping bridge deck, the low chord elevation is 742 feet. For the bridge opening, we can define the bridge opening with one of two methods: by span, which you could think of this as how wide the bridge opening is, or by bridge abutment stationing. In this project, we're going to define the bridge opening by span. We will define the reference centerline station as 1,000 feet, and we will define the bridge opening span as 100 feet. We need to define the same opening geometry for the downstream side of the bridge. Click the Copy to Downstream Bridge Opening button. This will duplicate the specifications from the upstream bridge opening to the downstream bridge opening. In addition, we need to define the bridge support piers. The support piers are 2 1/2 foot in diameter, and they are spaced 30 foot on center. Click the Build button, and the software will build the bridge opening. As I mentioned earlier, the bridge deck is sloping. So from the drop-down selector, choose Deck Roadway, and click the Upstream tab to see the geometry for the upstream bridge opening. Next, select the low chord elevation point that needs to be revised to account for the sloping roadway deck. We will change this value from 742 to 743.2. You can see that the bridge deck low chord is now sloping. We are going to duplicate this elevation value on the downstream side. Right-click on the value and choose Copy. Then, choose the Downstream tab. Select the value to be changed, and then right-click and choose Paste. You can see the bridge geometry on the downstream side is now sloping. Next, we can see that the bridge piers are not tall enough. We need to fix this issue. From the drop-down selector, choose Bridge Piers. You can see from the displayed panel that the selected bridge pier is highlighted in the bridge opening plot. We can see that the top of the bridge pier is currently at an elevation of 742 feet. Instead of trying to determine what the top of the bridge pier elevation needs to be to intersect the bridge low chord, we will have the software do that automatically. I am going to define an elevation of 750 feet, which is above the low chord, and in fact even above the top of the bridge. The software automatically trims the top of the bridge pier to the low chord geometry. Let's do the same for the downstream bridge opening by clicking on the Copy to Downstream button. And let's do that for all the other bridge piers by clicking on the Copy Geometry to All button. At last, we are finished. Next, we need to account for the losses created by the bridge piers. From the drop-down selector, choose Bridge Methodology. In this panel, for the Low Flow Computational Method section, turn on the Momentum and Yarnell computational methods. For the Momentum computational method, we need to define the pier drag coefficient. Click the Lookup button to see a table that lists pier drag coefficients. This bridge has round piers, so copy the round pier drag coefficient and paste it into the Momentum computational method entry. For the Yarnell computational method, we need to define the pier shape coefficient. Again, click the Lookup button to see a table that lists pier shape coefficients. These bridge piers are twin-cylinder piers without a connecting diaphragm between them. So copy the appropriate pier shape coefficient and paste it into the Arnell computational method entry. Next, we need to account for the ineffective flow area at both the upstream and downstream face cross-sections created by the roadway embankments. If we do not define these ineffective flow areas, HECRAS will consider the entire cross-section available for flow conveyance at the bridge face, and the computed water surface elevation will be lower than it should be, resulting in an incorrect solution. We need to tell the software at the upstream and downstream face cross-sections where the water is stagnant and not effectively conveying flow. From the drop-down selector, choose Ineffective Flow Areas. The roadway crossing is a bit more complicated than most because of the vertical curve associated with the roadway crossing. To account for this vertical curve, choose the Multiple Blocks option. Next, click the Draw button. Then to better see the roadway geometry, choose the Maximize Plot button. Click and drag rectangular blocks to define the ineffective flow areas. By using multiple overlapping blocks, we can approximate the ineffective flow area that is represented by the roadway vertical curve. However, we are limited to 10 blocks at a cross-section, a limitation in the HECRAS software. Therefore, we need to be careful in our placement of these blocks. Notice that we do not butt the ineffective flow area directly to the edges of the bridge opening. This is because the upstream and downstream face cross-sections are a small distance upstream and downstream from the actual bridge opening. This small distance allows the flow to transition through the bridge opening. By providing this small horizontal distance between the adjacent ineffective flow area and the bridge opening edges, we account for this transition in the computations as the flow contracts and expands. If you make a mistake or need to adjust any of these blocked ineffective flow areas, choose the Graphical Edit button. You can then grab the edges or corners of the ineffective flow areas and move them to where you want them to be. Finally, HECRAS does not like ineffective flow areas to overlap each other. In fact, HECRAS will prevent you from computing the analysis for a model that has overlapping ineffective flow areas. So click the Restore Plot button, and then click the Fix Overlapping button. The software automatically trims the ineffective flow areas to correct for the overlap. We also need to define the ineffective flow area at the downstream face cross-section. Because the roadway vertical curve geometry is the same for both the upstream and downstream face cross-sections, and we defined a common datum for the horizontal stationing, click the Copy to Downstream Cross-Section button. The software will duplicate the ineffective flow area for the downstream face cross-section. We have now completed defining the bridge data, and we can close the Bridge and Culvert Data dialog box. The next thing we need to do is change the contraction and expansion loss coefficients to account for the additional energy losses as the flow transitions through the bridge opening. These additional losses are accounted for at the downstream face cross-section, upstream face cross-section, and the approach cross-section, but not at the exit cross-section. This is because of the way that HECRAS computes the water surface elevations for a steady flow model. HECRAS computes the backwater from the current cross-section to the next upstream cross-section. To account for this change in contraction and expansion loss coefficients, select Cross-sections, and then Edit Contraction and Expansion Coefficients. In this dialog box, we can define the coefficients manually. However, the software can do it automatically. Click the Default button, and the software will review the roadway crossing structures contained in the model, whether they are bridges or culvert crossings, and automatically assign the appropriate contraction and expansion coefficients at the correct cross-sections. Then, click OK to store these changes. Let's zoom into the roadway crossing. We can see where the bridge abutments and piers are located. Let's change to a 3D view. We can see the structure in a perspective view and can see how the roadway geometry, low chord geometry, bridge opening geometry, bridge piers, and ineffective flow areas define the roadway crossing. At this point, we are ready to run the HEC-RAS hydraulic analysis for the roadway crossing. Thank you for watching this video on YouTube. If you like this video, please click the like button. And make sure you subscribe to our YouTube channel to stay up to date with all the engineering tips and tricks videos that we publish. And you can click on any of the videos around this one to watch more engineering tips from us. Finally, if you have not yet started using HEC-RAS, make certain you visit our website at CivilGEO.com and download a copy of HEC-RAS to try out. Thanks so much for watching.